So last time we had started talking about implicit differentiation. Seems like it'd be worthwhile to do a few more examples to just make sure we're good with it. So let's look at something like this. Let's say we want to find dy dx, or you can call it y prime, either way, for the following equation. X to the fifth plus y to the third plus tangent of y equals. To make sure I'm not doing the same exact problem I did before. I'm not doing the same exact problem, but it's very similar. Let me change it up a little bit. Sorry. Thank you. Let's do cosine of xy plus e to the x. So again, whenever we're always thinking about, really what I say is like, if someone says find the derivative and they give me this garbage and they don't say use implicit, and there's like find the derivative. The clue here that we need to use implicit differentiation is all these x's and y's jumbled up together. Right? We can't solve for y as a function of x. It's impossible. So that's kind of the clue. And what we're going to do with that is say, well, we're just going to differentiate everything, remembering or assuming, thanks, Kate, that y is a function of x. So when I take the derivative of x to the fifth, okay, we're going to get 5x to the fourth. When I take the derivative of some stuff cubed, we're going to get 3 times our stuff squared times the derivative of the stuff. The derivative tangent of some stuff is secant squared of the stuff times the derivative of the stuff. Derivative cosine of x times y. Well, I've got the derivative cosine of some stuff, but my stuff is a little more complicated. My stuff isn't just y, it's more complicated. So I have to be a little more careful. Derivative cosine of a thing is negative sine of the thing. I have to multiply by the derivative of the thing. And for the derivative of x times y, I'm going to have to use the product rule. So it's going to be the derivative of x, which is 1, times y, plus x times the derivative of y, plus the derivative of e to the x, which is e to the x. Questions about this first step? This is kind of the key step, right? Everything after this is, it's still terrible, but it's just algebra after this. I mean, it's terrible algebra. Thank you, thank you. So now we're going to, so whenever you have this kind of deal where you have something times a piece where one of the parts has a y prime and the other part doesn't, we really have to distribute that before we can do anything else. So we're going to distribute that negative sine of xy. Thank you. We're going to get 5x to the fourth plus 3y squared y prime plus secant squared of y times y prime equal to negative sine of xy times y minus sine of xy times x times y prime. And yeah, this y and this xy prime need to be outside of the sine function. So definitely, when you've got sine times some other stuff, you need the stuff inside the sine function for sure in parentheses to make sure it's clear what's what. All right, now it's just terrible bookkeeping. There's all my y prime terms. I'm going to bring them all to the same side. Let's bring them all to the left. And so here's what I would suggest. We know we're going to bring all the y primes to the left, or whichever side is convenient. And we know we're going to factor out a y prime. We can probably do that in one step, because I can see that from each of those terms, if I factor out the y prime, I'm just left with whatever else isn't y prime. So I'm going to pull this over here. I'm going to factor out the y prime. When I do, thank you. Can you see something? So I'm sorry, but I have to ask you to leave. You can come on. You can watch class on Zoom then. You're welcome. So we're bringing this over, and then we're factoring out a y prime from this term, and this term. So I'm going to have a positive sine of xy times x. I'm going to have a positive 3y squared, and a positive secant squared of 1. And then on the right-hand side, I have my negative sine of xy times y. I would probably put the y in front, actually, to be honest, and write it as negative y times sine of xy. I have a plus e to the x and I have a minus 5x to the fourth coming to the other side. And lastly, we're going to divide by all of this. Y prime equal to all of that, negative y times sine of xy plus e to the x minus 5x to the fourth over, I would probably write this as x times sine of xy plus 3y squared plus secant squared of y. Whew. Okay. It's a process. It's literally the same like 3 or 4 steps every time. Differentiate both sides. If you have to, you distribute things. If you've got like a y prime and not y prime, and then you group all the y primes on one side, factor out what there is, divide by what there is. It's just the same thing every time. Questions before we do a couple more? Yeah, question.
I'm confused with like the negative sine xy. How you go like times 1 times y plus x times y.
Sure. So when I took the derivative of cosine of xy, so the derivative of cosine of xy, so I'm going to use the chain rule, and the derivative of cosine of some stuff is negative sine of the stuff times the derivative of the stuff. But when I take the derivative of xy prime, sorry, when I take the derivative of xy, what rule do I have to use? Product rule. So I still have the negative sine of xy, and then the derivative of xy, I have to do the product rule. So if you want, or you can think of x as f and y as g, and I know it's going to be f prime g plus f g prime. So what's f prime? What's the derivative of x? Everybody knows the derivative of x. It's 1 times g left alone, which is y, plus, now we want f left alone, which is just x. And what's g prime? Thanks. What's the derivative of y? It's the derivative of y. So that's what's going on there, okay? Does that make sense? Okay, and then, so since we have negative sine of xy times all that, and one of those terms has a y, or sorry, one of those terms has a y prime and one of them does not, we need to kind of break that up because we're trying to isolate all the y primes together, and having this makes it kind of so you can't do that until after you distribute. So that's why we're distributing there. Other questions about this? It's usually just a lot of gross algebra, to be really, really frank. Let's look at least a couple more. So there's this kind of classic example that some of you have a homework problem on, which I'm happy to look at. It's called the Folium of Descartes. It is in many textbooks. It looks like, not that, don't do that. It looks like that. It's x cubed plus y cubed equals 6xy. And the only points I know that are on it for sure are the points 0, 0, which is right there. I'm trying to click on it, but I can't. Whoops. And the point over here, 3, 3. So one of the questions on this particular, so here's what I would ask for this first one. So here's what we've got. I just have this paper right here in front of me. So we could totally find the tangent line at lots of places. So we could find the slope of the tangent line at, well, so here's where you have a choice. You can either be specific or general. I'm going to be specific and find the slope of the tangent line at the point 3, 3. And I'm going to do this in the, what I consider to be kind of the easy way. So I'm still going to do my same first step. Step 1, differentiate. So the derivative of x cubed is 3x squared. Differentiate this. The derivative of y cubed is, well, the derivative of stuff cubed is 3 times my stuff squared times the derivative of my stuff. And the derivative of 6xy, so you can, I personally like to think of it as 6x times y, but you could also think of it as 6 times the product xy. Either way is going to work. I like grouping the 6 with the x, because then I'm like, okay, the derivative of 6x using the product rule, right? 6x, sorry, I should say, using the product rule on 6x, which is my f, and y, which is my g. The derivative of 6x is 6 times y, plus, now we leave the 6x alone, and multiply by the derivative of g, or derivative of y, which is y prime. I find it nice that way. But if you prefer, you could also think of it as 6 times xy, and then the 6 just kind of hangs out. And the derivative of xy is 1 times y plus x times y prime. It's literally the same thing either way. But I like this better because, one, I don't have to do any distributing afterwards. So I think this is better. Now, if you're only asked to find the slope of a tangent line at one particular point, you don't have to do all the terrible algebra of solving for y prime in terms of x and y. You can immediately plug in your point. X equals 3, y equals 3. Let's see what happens when we do that. So plug in 3 for x, I get 3 times 9, which is 27. I plug in 3 for y, I get 3 times 9, which is 27 times y prime. On the right-hand side, I get 6 times 3, which is 18, plus 6 times 3, which is 18, y prime. So subtracting 18y prime, I get 27 minus 18, which is 9y prime. And 18 minus 27 is negative 9. So it looks like at the point 3, 3, the slope of the tangent line is what? Negative 1. So at 3, 3, slope of the tangent is negative 1, which is totally backed up by my drawing here. If you tried to draw the tangent line there, it definitely looks like that slope is probably negative 1. And if you want a more precise drawing, come on. I have the line there, I must have deleted it. So here's the actual tangent line. Totally going right to that point over there. Oh, too close. Back up. All right, but there's the point 3, 3. And there's the tangent line y equals 6 minus x, which totally has a slope of negative 1 going to that point. Now, a couple things to address. This is not a great process to use if you have to find derivatives at more than one point. And this is only really good if you're finding the derivative at one point on the graph. But if you have to find the derivative at like 3 different spots, like if you want to find also 0, 0 or something, this is not excellent. But it's perfectly great if you want to find the derivative at one particular point. The other thing I'm going to mention here is that on this homework assignment for Dr. Didell's class, he asked a question about finding or estimating the slope of the tangent line of the point 1, 1. I feel like that's a typo because the point 1, 1, not on the curve. I thought he might have meant like maybe you try and find the tangent line that goes through the point 1, 1 that's to the tangent to the curve, but that's not really good. So I'm pretty sure that's just a typo if you're worried about that. Okay. Let's look at another example that's similar-ish. So let's look at, say, oh, where'd you get the example that I made up here? Let's say we have this equation, x cubed plus y to the fourth equal to 2x squared minus 2y cubed. And we want to find the slope of the tangent line, well, respective tangent lines at the points. And what do we got here? 2, 0, 0, negative 2, and 2, negative 2. Which I should mention are all points on this graph, right? Not like 1, 1 on the previous one, which isn't right. If you look at the previous function, it's pretty clear that if x is 1 and y is 1, that's not a point on the graph. And I will tell you, this is a common mistake teachers make all the time. I've made this mistake many times. They're like, oh, I'm just going to make up something, and I'm just ask them to plug in x and y. And I didn't think about the fact that the point x, y wasn't actually on the graph. It actually, I've seen people write that on a test before. So I would just go with it. They're usually trying to pick points that are easy. like maybe not pointing out the fact that the point is not on the thing, it might not be in your best interest possibly. So, but it is a mistake teachers make all the time, really, for sure. So these points, right? If you actually look, if x is 2 and y is 0, you get 8 here plus 0, you get 8 here minus 0. Oh, it's on there. And if x is 0, y is negative 2, you get 0 plus 16. 0 minus 2 times negative 8 is plus 16. And this point's also on there. Really, I just looked at the graph. I didn't actually think about it. So I could, well, the first step is the same no matter what. We're going to differentiate. So I'm going to get 3x squared plus the derivative of y to the fourth, or some stuff to the fourth, is 4 times y cubed, y prime, equal to 4x minus the derivative of 2y cubed is 6y squared times y prime. Now, I want to say a couple things, actually. Thing one, I mean, we could just go start plugging in these points and find the various tangent lines, but I don't think it's really in our interest. Because it's like, I'm trying to save myself work, right? If it's only 1 point, sure, save yourself all the work in the world. But if it's multiple points, I really feel like it's probably going to make more sense just to solve for y prime. Let's bring the y primes to the left. We got 4y cubed times y prime plus 6y squared times y prime. Why did I pick the left this time? Because the left is the more normal choice usually, but really I'm usually picking the side where more things are positive. That's really the way I'm deciding which side to pick. It doesn't actually matter, but I just think it looks nicer. On the right, we're going to have 4x minus 3x squared. So then when I factor out a y prime, 4y cubed plus 6y squared equal to 4x minus 3x squared. And then finally, y prime equals 4x. We got to do the thing. It's cool. 4x minus 3x squared over 4y cubed plus 6y squared. And almost never, this time included, there's almost never like a time where you can factor and cancel anything from the top and the bottom. There are rare exceptions, but they are rare. Great. So let's see what our slopes are. So at the point 2, 0, we get a slope of, well, I'm going to plug in 2 for x and 0 for y. Well, that's not going to be good. I'm going to get 8 minus 3 times 4 is 12 on top. And on the bottom, I'm going to get 0 plus 0. What does that mean? Well, literally, 4 over 0 is undefined. If this, so I really should have asked, let's find the equation as well. If the slope's undefined, what kind of line do you have? It's a vertical line. And which makes sense, right? Because if you think about this, you can literally think about this as the rise over the run. This has some amount of rise and 0 amount of run. That's a vertical line. So this line here is vertical. And the equation of the line would literally be x equal to the x coordinate, which is 2. It's kind of neat. Also something to be aware of, and this is something I've seen over the years, is that if you were trying to plug in this point in particular before doing all the work, you do run into problems. So if we actually plugged in 2, 0, I'm just going to show you. We plug in 2, 0. On the left-hand side, we get 0y prime plus 0y prime equal to 8 minus 12. So I get 0 equal to negative 4. If you were doing that and that happened, that almost always means you have a vertical line because you have an undefined slope. So if you run into this trying to do it the shortcut way, it's fine, but you should probably go back and do it the longer way because like it can be a little bit, it feels a little unsure. Like maybe that's what I have. Maybe not. Let's see what we've got at the other points. So at the point 0, 2, our slope is going to be, well, now we're putting in 0 for x, we're going to get 0 on top. Putting in 2 for y, we're not going to get 0 on the bottom. We're going to get something. It doesn't really matter, but it's Oh, thank you. Yes, -2. Thank you so much. Yeah. I'm plugging in -2 and I'm getting, well, maybe I will get 0 now. Let's see. 4 times -2 cubed plus 6 times -2 squared. It's going to be not 0 on the bottom. So I get 0 over not 0, which is 0. I don't really need to do the work and say that's -32 plus 24, which is -8 on the bottom. Once you know the bottom isn't 0, 0 divided by non-zero is always 0. So here, the equation of the line would be y equal to -2, because it's a horizontal line with a slope of 0. So it's just going to be whatever the y coordinate is, which is -2. Okay, now for the most interesting one. We actually get a non-zero, non-undefined slope at the point 2, -2. Well, again, we're going to plug in. In fact, we already know what we're going to get. Because when we plug in 2 for x, we get 8 minus 12 on top. We plug in -2 for y. I guess I should have done the work. Plug in -2 for y, we get -32 plus 24 on the bottom. It ends up being -4 over -8, which is positive 1/2. So the slope is 1/2. And then let me come back to that question there. So the slope is 1/2 and we get y prime. So yeah, sorry. If we want to write the equation, we can write it as y minus -2 equal to 1/2 times x minus 2. Or if you want to solve for y equals 1/2 x minus 1 minus 2 is -3. Kind of neat. And just to kind of, well, fine. So there's a question that says, why do we have y prime after taking the exponent of y? I'm not sure what you mean by the exponent of y. Because what I think of when you say the exponent of y is like e to the y power, which I don't think I've written down so far today. Do you mean something else? Uh-huh. That might be what they mean. Let me send them a message to you. Oops, can I type? It's good we have this little like keyboard thing on here, but it makes it harder to type. So 1 sec. But to generally answer the question, again, we are making the assumption that we're always assuming that y is a function of x. Yeah, so sure. So why, when we took the derivative of y to the 4th, did we get 4y cubed times y prime? Well, the reason is because we're really pretending like y is some function of x. So maybe, although it's not true, maybe y is equal to x squared plus sine of x. I know that's not really the case, but we can just pretend for a minute. So then if I had y to the 4th, well, that's really going to be x squared plus sine of x to the 4th. And the derivative would be, well, the derivative of stuff to the 4th is 4 times your stuff to the 3rd times the derivative of your stuff, which is 2x plus cosine of x. But that's really just 4 times y cubed, right? Y is our x squared plus sine of x times y prime, the derivative of y. Y prime. That's why we were always, when we take the derivative of something with y, multiplying by y prime, because we were always thinking, oh, y is a function. I mean, okay, y is not really a function of x, but it's close enough. It depends on x heavily. So we're pretending like y is a function of x, and we're saying, oh, we're going to have to use the chain rule. The derivative of some stuff to the 4th power is 4 times my stuff to the 3rd times the derivative of the stuff. That's always the case with implicit differentiation. It is kind of neat. Like we definitely, so back in my day, probably couldn't have graphed this ever. Like I have no idea what this graph looks like, but Desmos is awesome. So let's turn you off. There it is right there. Is it? I feel like I missed something there. X cubed. Oh, why this? That doesn't seem right. It really doesn't seem right. X cubed plus. It looked too nice. I was definitely looking at a different function earlier. Did I change my y to the fourth to y to the fifth? Oh, thank you. Thank you. Yeah. Okay. I was like, I know it didn't look that nice. Plus, I don't have all the right points. Right? I said it goes through some points. It's clearly not going through there. There we go. Much more interesting looking. So check out that. That is literally what the graph of this equation looks like. And you can see the points 2, 0, 0, -2, 2, -2. And you can see the tangent lines. You can see y equals -2. Oh yeah, it's totally tangent there. Or you can see x equal to +2. Totally tangent there. Or you can even see y equal to 1/2 x -3. Oh yeah, totally tangent there. So, I mean, we're not like making this up, right? These things actually do what we say they're doing. It's just a weirder process. But implicit differentiation really does give you the derivative, which you can use to find the slope of the tangent line. But it's kind of funky, right? Because this graph totally has two different, or maybe more, but at least two different tangent lines at x equals 2, right? There's this tangent line here when x is 2 and y is -2, and there's this other tangent line over here when x is 2 and y is 0. So clearly not a function, this original graph, but definitely has tangent lines that make sense to talk about. Kind of neat. Oh, come on, go away. Want to do it that way, we'll do it that way. Okay, so what do we use this for? Well, it's a good question. What's going on over here? Okay. We could do more examples. I feel like we should not do more. We could do more examples, but well, we're going to do more examples. They're just going to have some more context to them. So one of the main ways we kind of think about implicit differentiation is talking about related rates. So related rates, I feel like math is not very innovative when it comes to names, right? We're just like, here's the thing. We're going to call it, let's call it the thing that it is. Related rates literally mean you've got rates that are related. One thing is going to be changing, and we're going to ask how another thing is changing. Here is a very common example. The radius of a circle. I think about like throwing a stone in a pond, ripples. Ripples get bigger, as time goes on. I'm going to say the radius of those circular ripples increases at a rate of 2 inches per second. When the circle has a radius of 5 inches, how fast is the area of the circle increasing? Before we answer this question, I just want to point out it really, right, the rate of change, the rate that the area of the circle is increasing is not always the same. Let's just think about it a few moments. So you throw the rock in the pond, and it's a little scrooge. And then after 1 second, what's the radius of my circle? 2 inches. So we got a circle. It's 2 inches in radius, and the area is 4 pi, right? It's pi r squared, pi times 2 squared is 1 pi. Okay, but then after another second, what's my radius going to be now? 4 inches. And the area is going to be pi times 4 squared, which is 16 pi. And then after another second, the radius is going to be 6 inches. And the area is going to be 36 pi. So not that these are exact instantaneous rates of change, but from the first second, right, it looks like, okay, in 1 second, the rate of change of area looks to be 4 pi inches squared per second. Right? We went from 0 inches squared to 4 pi inches squared. And then from here to here, we're going from 4 pi to 16 pi. We're increasing by 12 pi inches squared per second. So the rate of change of the area of the circle is bigger and bigger as the circle gets bigger and bigger. Every time the circle increases its radius by 2 inches, you're adding a lot more circle at the outer edge. Right? When I increase the circle by another 2 inches, I'm adding a whole lot more out here than I was when I increased this circle by 2 inches. So how do we deal with this? Well, we're going to use some implicit differentiation. So when I'm thinking about related rates, I usually think about a few things. The first thing is usually what is changing? Now, I know a lot of things are changing in this setup. You can say something, well, so the answers I want for this particular one are what's changing, the radius of the circle, and the area of the circle. Are those the only things that are changing? No. Time is changing, the circumference is changing, the diameter is changing, but I'm trying to focus in on the things that we actually care about. And the problem is telling me how the radius is changing, and the problem is asking me how the area is changing. They kind of want to just narrow it down to the things we were told about and the things we want to know about. All right, and so how is the radius changing? Well, the way we're going to write that, and this is definitely a time where we almost always use the Leibniz notation. We're going to say that the radius is changing. We're going to write that as dr dt. It's the rate of change of the radius with respect to time, or how r is changing as time is changing. Sorry, you guys want to see that probably. And we know we were told that the radius is changing at a rate of 2 inches per second. We want to know how the area is changing. So I'm going to say that area is capital A and radius is lowercase r. And I want to know what dA dt is. I don't. That's what I'm trying to find. So first step, identify what's changing. Second step, find an equation relating those two things. Relate the variables with an equation. Most of the time, not all the time, but a lot of the time, this is going to be some sort of geometry formula. Like the area of a circle is pi r squared. That's the formula that relates these variables. Now, here's the important step that people kind of get thrown off by. We're going to differentiate both sides but we're going to remind ourselves that both area and radius are functions of time. Right, so even though I haven't written that down on this, right, we know that as time changes, the radius changes. As time changes, the area changes. Both area and radius are dependent upon time. So it is implied, or it's implicit, that area and radius are functions of time. So we're going to differentiate both sides with respect to time. So it's just like how in the previous work we were doing, when we said, okay, I'm going to take this terrible equation and I'm going to pretend like y is a function of x. I'm going to differentiate it. I'm going to get y prime because I'm going to have to use the chain rule. It's the same idea over here. I'm going to take this equation and pretend like both A and R are functions of t. When I differentiate this, I have to be a little bit more careful than just saying it's not just going to be 1 equals 2 pi r. 1 because that's wrong, but 2 because, well, 2 because it's wrong. Because we know that really you have the following. I'm going to take the derivative of A. Okay, I know this is not an easy question to answer because the answer is kind of just, it's kind of, I'm going to tell you the answer when I ask the question. What's the derivative of A? It's the derivative of A, which I'm going to write as dA dt. Because it's really, I should say, what's the derivative of A with respect to time? Oh, it's dA dt. It's the change in A over the change in t. Okay, so now what's the derivative of pi r squared with respect to time? Well, I have pi times some stuff squared. And the derivative is 2 pi times my stuff times the derivative of the stuff. That's the key step, is that when you, after you get this equation relating the variables you're interested in, you differentiate both sides. And it's almost, there are some exceptions, especially, actually, there's some good biological examples in this class where it's not time, but most of the time, the variable that things depend on is time. And so you're going to differentiate both sides with respect to time. And then after that, and definitely it has to be after that, after differentiation, then you plug in what you know. Plug in known values, solve for what you want. Occasionally there's an extra step in between. Actually, no, there's an extra step between step 2 and 3, but we're not there yet. So here I'm going to plug in the fact that I know that dr dt is 2 inches per second. And I know that r is 5 inches. I know that's not on this page, but the question, if you recall, said when the circle has a radius of 5 inches, how fast is the area of the circle increasing? You guys can see it either. Sorry. So we know that r is 5 inches. Dr dt is 2 inches per second. I personally would not plug in the units when I do it right away. I would just wait till the end. But you can plug in the units right away. You can say, okay, I'm going to plug it in and I'm going to get dA dt equal to 2 pi times 5 inches times 2 inches per second. And then 2 times 5 times 2 is 20 pi. And I've got inches times inches, so inches squared per second. And the unit should make sense, right? How area is changing should be a measure of area, inches squared per a unit of time, per second. You also could have just said, I'm going to just plug in the numbers and say dA dt is 2 pi times 2 times 5 and get 20 pi. And then ask yourself at the end, what do the units have to be? Well, I know it's how an area is changing per time. My length is measured in inches, so my area is measured in inches squared, and my time is measured in seconds. So if it's how a length is changing per time, it's some length per time, like meters per second, or miles per hour, or inches per second. If it's an area per time, it's like inches squared per second, or miles squared per hour, or whatever. But it's always just the right power. And if somehow some volume is changing, it can be like cubic centimeters per minute, some length cubed per some time. So what I'm trying to say with all those words is that you can wait till the end to just figure out what the units need to be. Or you can plug them in before and actually multiply it out. Either way, it's fine. It just feels like a lot of writing doing it this way sometimes. Questions before we do another one? Ooh, actually, a follow-up question. How fast is the circumference changing? At the same moment? Well, I'm going to do the same sort of thing. I'm just going to find, instead of, so I still know these things. I don't really care about area anymore. But now instead of having an equation that relates radius and area, I need the equation relating radius and circumference. So circumference is 2 pi times the radius. And now when I differentiate, again, differentiate with respect to t, dc dt equals, what's the derivative of 2 pi r going to be? 2 pi hangs out, and what do I get there? You guys can't see the face I'm making on my face. I'm kind of like, I'm making a terrible face. I'm making a, what do you think it is kind of face? It's going to be dr dt. Right, the derivative of r is the derivative of r. So then we plug in what we know. We know that, again, r is 5 inches and dr dt is 2 inches per second, but there's nowhere to plug in r equal to 5 inches. That's okay. It happens sometimes. What that means, I get dc dt equal to 2 pi times 2 inches per second, which is going to be 4 pi inches per second. What that means is it doesn't actually matter how large the circle is. If the circle is increasing its radius at 2 inches per second, the circumference is always increasing at 4 pi inches per second, which kind of makes sense, right? Because if the radius increases by 2 inches, you've made the circumference just that much larger. But that's going to be the same no matter if you increase from like 6 inches to 8 inches, or if you increase from 60 inches to 62 inches. Either way, you're still increasing the circumference by the same amount, because circumference is a linear function of radius, right? Circumference is just a multiple of radius, whereas area is some multiple of radius squared. And that's all the difference there. Okay, let's look at another example. Yeah, we got time for one more example. So let's look at this example. Next time we'll do some biology examples. So I'm going to say words and draw a picture because there's a lot of words right now. So Gabriella, we'll label with a G, is standing 6 feet from her sister Mia. I said I wasn't going to write the things, and I'm just writing the things already. Who happens to be holding a balloon? It's not going to go well for her. She lets go of the balloon. Sadness. He lets go. And the balloon rises at a rate of 4 feet per second. After 2 seconds, how fast is the distance between Gabriella and the balloon changing? So really, I should have said last time, the first step when you do a problem like this is if you need to draw a picture, draw a picture. And most of the time you want to draw a picture. So here's Mia, who had the balloon. Here's the balloon traveling upwards. And here is her sister Gabriella over here. And here is the distance between Gabriella and the balloon. And I've done this kind of intentionally. I've drawn the things that are changing dashed. That's not really typical. You could totally draw them. In fact, most people will probably draw them with solid lines. But the idea here is that you want to label everything. And we know that the distance between Gabriella and Mia is 6 feet. But these distances are changing, right, as time goes on. We're going to look at the instance, or the instant, after 2 seconds have passed. But in general, if something is changing in our picture, we should give it a variable name. I'm going to call this Y and this S. Great. So now I'm going to answer the usual first. So you can call this step 0 if you want. Wow, can I write step 0? Step 0, set up your picture. Label things that change with variables. Great. Now step one. What's changing? Well, we already know that, right? We're just going to write it out. So we know that y is changing. Y is the height of the balloon. We actually know how that's changing. The height of the balloon is changing at 4 feet per second. The rate of change of y, or the rate of change of the height of the balloon, is exactly that. We also know that s, the distance from Mia to the balloon, is changing. S is also changing. I don't really need to write the words S is changing, but not terrible. And ds dt is what we want to find. Great. Now we're going to write our equation relating the variables. And I should really point out, we also know the time is changing, right? Time is always kind of the underlying thing that's changing, not always, but most of the time. What I really say is when you want to write an equation, you want to write an equation relating the non-time variables. So we want to write an equation that has s and y and preferably nothing else. No, I should say no other variables. What, let me make it obvious here. What famous theorem springs to mind? Yeah, that one, the one that starts with a P. Pythagorean, 6 squared plus y squared equals s squared. And while you could totally solve for y or s here, why bother? It's more work. We're just going to differentiate both sides of this. What's the derivative of 6 squared? Oh, don't get caught up. 0. The derivative of y squared? You can say y prime, but really I will say most of the time when people do related rates, they really do write it as dy dt. I don't know why specifically for related rates, it just is what people do. And then the derivative of s squared is 2s ds dt. There's something I wanted to say right there. Maybe not. I feel like there was. I guess not. Anyway, so now we're going to plug in what we know. So we're trying to figure, oh, I know what I was going to say. Typically, when you're doing this, the rate of change you know and the rate of change you want to find should both appear in your derivative. If both of those aren't showing up, you've probably done something incorrect. So then we're going to plug in what we know. So I know y. Oh, do I know y? How high is the balloon after 2 seconds? Well, how fast is it going? 4 feet per second, 2 seconds. So it's going to be 8 feet high. So after 2 seconds, we know that y is equal to 8 feet high. So I'm going to have 2. I could cancel the 2's on both sides, but whatever. Times 8 feet times dy dt, which is 4 feet per second, equal to 2 times, oh, I don't know s. Shoot. Can I find s? I mean, I can, right? Because I know 6, I know 8 at this moment, right? It's not always 8 here, but at the time I'm interested in it is. And that's going to be whatever it is. So this is really a 3, 4, 5 triangle multiplied by 2. It's a 6, 8, 10 triangle. You could also use the Pythagorean theorem and plug in 6 and plug in 8 and solve for s and get 10. Oops, and I forgot my units. That's all right. So then divide both sides by 20 feet, and you get ds dt equal to 16 feet times 4 feet per second. This is the reason I don't really like to write the units while I'm doing it, because it's a lot of unit writing. So 16 times 4 over 20, the feet cancel, and you can reduce this, right? 20 and 4 cancel down to 5. So we're left with 16 over 5 feet per second. Or if you prefer, 3.2 feet per second. slower than the balloon is rising, which almost always is the case. If something's going straight up, the distance from some other object to it is going to be changing at a slower rate because that's going to be going kind of like you're measuring like this distance and it's not increasing as fast as just the straight direction of motion. So it is very, very typical to find that the diagonal distance to some object is increasing more slowly than the just how fast the object is moving. All right, it's 3:01. I should stop talking.